Hi, this is a presentation regarding the chi-square statistic, in which we'll be talking about the test for goodness of fit and independence using the chi-square statistic. First, we need to talk about what is meant by the term parametric. So, first, what is a parameter? Well, basically, a parameter is a population value, such as a mu or a sigma, that represents a population characteristic. So, if you think back to t-tests, ANOVAs, whatever you covered in EPSY 5380, whenever you did hypotheses, you stated mu equals 0, or mu 1 minus mu 2 equals 0 for the null hypothesis. And when you do that, all your hypotheses are concerning parameters rather than statistics, because you are trying to generalize to the population. And the parameter is a numeric value that represents a characteristic about the population, versus a statistic, which is indicative of a value of characteristic to a sample. So population has parameters, samples have statistics. So parametric tests are basically concerned with specific values about the population and generalizing to that population. So then we also have parametric versus non-parametric. So parametric tests have distributional assumptions. The one in point being normality, that there is a normal distribution of the data. Versus non-parametric, there are no distributional assumptions. In parametric, variables are measured on an interval or ratio scale, so at least an interval scale, and at times a ratio scale as well. And then for non-parametric statistics, variables are measured on a nominal or ordinal scale. And these non-parametric tests are sometimes called distribution-free tests, because there are no distributional assumptions, such as the requirement that data be normally distributed. So what are the assumptions of chi-square, which is a non-parametric test? The one that there's an independence of observations. You're already familiar with this from the assumptions of parametric tests. So that one falls over from parametric to non-parametric. And then also assumption of chi-square is the size of the expected frequencies must be 5 or greater. This is more of a rule of thumb. You can do an actual power analysis to kind of figure out what sample size may be required to do a chi-square analysis, but that's kind of out of the purview of this class. So the chi-square goodness of fit test. Basically, we use sample data to test hypothesis about the shape or proportions of a population distribution. So this is basically a one sample or one variable goodness chi-square test. So the chi-square goodness of fit test is really a one variable chi-square test. That's another way of thinking of it. So how well the sample proportions represent the population. So how well can you generalize your sample proportions, which are nominal or ordinal, to the population without being held to the distributional assumptions of parametric tests. Hence goodness of fit, so how well it fits, so it's goodness of fit. So what is the null hypothesis in the chi-square goodness of fit test? Well, we specify the proportion or percent of the population in each category. So for example, let's say your H sub O is that 90% of men and 10% of women agree to some survey question, etc. And there's basically two types of H sub O, or null hypothesis, for the chi-square goodness of fit test. One is the no preference test. And in the no preference test, that you're saying that there is no difference in the preference between, let's say, brand X, Y, and Z. So basically 1 divided by 3. So there's really no preference. So 1/3 H sub O would be that each one is preferred 33% of the time. And then there's also the no difference from a known population hypothesis as for the null. So the H sub O in this case would be that 60% favor and 40% oppose. And this is based upon previous population data. So like proportions for the European population are not different from the American proportions. So basically your past literature would guide you on whether or not it would be a no preference null hypothesis or no difference from a known population. So what do the data for goodness of fit look like? It's actually quite simple. You have your observed frequencies, which are your F sub O. For example, you have category A, B, and C, and this is the data you collect. You can say that 15 individuals preferred A, 19 B, and 6 C. And so the total N would be 40, so 15 plus 19 plus 6. And what are expected frequencies? So the goal of the chi-square goodness of fit test, or the chi-square GOF, is to compare observed frequencies, which is the data you collect, with the null. And with that said, you need to determine how well the data fit the distribution specified in the null. So whatever your null states as what should be the distribution of the data. For example, you may propose that category A would have 25% agreement, category B would have 50% agreement, and then category C would have 25% agreement. So this would be no difference from a known population. So this would be meaning that your literature indicates that this would be the distribution between A, B, and C. And based upon those numbers, you would then calculate the expected frequencies. So if your null is true, the expected frequencies would be as follows. Remember that your total N was 40, so 25% of 40 is 10 individuals in category A, and then for category B, it says the null hypothesis that would 50%. So 50% of 40 would be 20 individuals in category B. And then last but not least, the null hypothesis stated that 25% of 40, 25% of the individuals would endorse category C, which is 10 individuals again. So 10, 10, 20. Those would be your expected frequencies. So you have your observed, the data you collect, and then you have your expected based upon whatever specifications you make in your null hypothesis. If it was a no preference null, it would just be a third, because there's 3 categories. So you would do 0.33 multiplied by 40. So basically the expected frequency, or F sub E, is the percent multiplied by N for the chi-square goodness of fit test. Values predicted from the null according to the sample size. So basically based upon your total sample size. So if you had 40, so it would be 40 in the observed, then you'd be 40 multiplied by the percent. And so the question remains, or the question that would come up would be, logical question would be, how would the F sub E, the expected frequencies, be different for a no difference versus no preference hypothesis? Well, the expected frequencies in a no preference hypothesis would literally be all the same. It would be all the same percentage, because you're saying that there's no preference among the 3 categories. So if it was each third, a third, a third, a third, the expected frequencies would have the same percentage. So the actual chi-squared statistic we're looking at how well the F sub O, the observed frequencies, fit the F sub V, which we are hypothesizing in our null. And the formula for chi-square is quite simple. It's the F sub O, the observed frequency, minus the expected frequency for each cell, squared over the expected frequency for that cell, summation of all the cells together. So you basically look at each cell. So if you have 3 categories, you have 3 cells to calculate for the chi-square goodness of fit. And after you calculate your chi-square statistic, you need to then compare it to a critical value. And how you do that, you have a chi-square distribution for this in almost any statistics book, but certainly in field, where the degrees of freedom is C minus 1 for the chi-square goodness of fit test. So C being the columns. So if you have 3 columns, then your degrees of freedom is 3 minus 1, which is 2. And then after you calculate the cut, you compare it to the critical value. And so here it is. So you would look at degrees of freedom 2, and it shows you the critical value for P equals 0.05, and then P equals 0.01. So for 0.05, it would be 5.99, and for 0.01, it would be 9.21. So not too difficult. So let's do a hypothetical example. Let's say a psychologist asked 50 participants to hang an abstract painting. And of those participants, 18 did top up correct. So they did it the correct way. 17 did it bottom up, 7 did it left side up, and 8 did it right side up. The H sub O would be, in the general population, there is no preference for any specific orientation. Thus, the 4 possible orientations are selected equally often, and the population distribution has the following proportions. So that would be for the null. And so writing it out, that's how you would say it above. But by diagram, you would say 25%, 25%, 25%, 25%, because there's 4 columns at play here. So for the alternative, you could state, in the general population, one or more of the orientations is preferred over the others. We're going to go ahead and set alpha at 0.05. Let's go ahead and locate the critical region, but first, what is our degrees of freedom? Degrees of freedom is C minus 1, and we have 4 columns, so degrees of freedom is 3. Our alpha level 0.05, and so what is our actual critical value for the chi-square? So for degrees of freedom 3, because remember it's C minus 1 and we have 4 columns, it would be 7.81. So 7.81 would be our critical value that we need to exceed. Then we need to calculate first our F sub E, our expected frequencies based upon the null. Now we already have our observed frequencies because that's the data we actually collected, but we need to calculate our expected frequencies. And to jog your memory, the null was that there was no preference among the 4 categories, so it would be 25% in each expected cell, expected frequency for each cell. So the expected frequency for each cell would equal 12.5. So 1/4 multiplied by 50 for each cell. So 12.5, 12.5, 12.5. Now we can calculate our chi-square. It's the same formula that we just discussed. So the F sub O minus F sub E for each cell. So where did you have 18 minus 2.5? 12.5 squared. But where does that 18 come from? It comes from our original data, the observed frequency. So, and then the 17 and the 7 and the 8 all come from the original data, minus the expected frequency, which comes from our null of what we hypothesized to be true, that there'd be no preference among those categories. So then you do the math and you end up with a chi-square test statistic value of 8.08. And if we remember correctly, that certainly exceeds our critical region value. So we make a decision. Well, if our 8.08 exceeds the critical region value, which I believe was 7.81 off the top of my head, we certainly reject the null at the 0.05 level. So we reject the null that it's all equal across the different categories. So are some orientations more often selected more often than others? Certainly so. Certainly so. Okay. Chi-square test for independence. Now this is a little bit different than the chi-square test for goodness of fit, because goodness of fit is where you just have one variable, with a number of columns, a number of levels to it. Chi-square test for independence is when you're comparing two variables or more, but we won't get into more than two. We'll just talk about two today. So the chi-square test for goodness of fit is for one variable, and the chi-square test for independence is for two variables. So for example, we can look at this one, the association between color choice and whether or not you're an introvert or extrovert. Identify yourself as either. So saying, well, maybe extroverts are more likely to pick red, which kind of looks that way from the data, just visually looking at it. My ocular inspection. So test for independence. So what does independence mean? It means that there's no consistent or predictable relationship between the two variables. So that would be your null. That there's no consistent, predictable relationship between these two nominal or ordinal variables. So for the case of the color preference and personality type, the H sub O would state there is no relationship between color preference and personality, or that there is no difference between the distribution of color preferences for introverts and the distribution of color preferences for extroverts. I like the former hypothesis rather than the latter. I think the latter is kind of verbose. So observed frequencies are easy, but what about expected? Because remember, your observed frequencies are the actual data you collect. So expected frequencies, let's get into that. First, you need to calculate your row and column totals. Then you determine your percentages by color. So percentages by color, you would say, well, that 100 out of 200 total, regardless of whether they were introverted or extroverted, selected red or preferred red, so that's 50%. And then 20 out of 200 selected yellow, so that's 10%. And then 40 out of 20 accepted, preferred or endorsed green, which is 20%, and the same for blue, which is 20%. Now we then look at per introverts versus extroverts. So for the sample of introverts, there's 50 introverts in the sample. We calculate the expected frequencies. So we're saying that 50% of individuals should choose red regardless of whether or not they're an introvert or extrovert. So the expected frequency would be 0.5 multiplied by 50. So we should have an expected frequency in that cell of 25 individuals who are introverts who selected red. Then for the expected frequency for yellow is 10%. So it'd be 0.10 multiplied by 50, which is 5. Then the expected frequency for green would be 0.20 or 20% of 50, which is 10, and the same for blue, 10 again. Then we do the same thing for the sample of extroverts, which we have a significantly larger sample of 150 of them. And you do the same thing, and you end up with 75 for red, 15 for yellow, 30 for green, and then 30 for blue. There's also a simple formula for determining the expected frequency for any cell. So F sub C multiplied by the F sub R, where C refers to column and R refers to row, divided by N. So for our example, you could take 20 multiplied by 50 over a total N of 200, which would give you the expected frequency of 5. That's for the introverts with yellow, I believe. So the formula for chi-square for the the actual chi-square calculation for chi-square goodness of fit and the chi-square test for independence stays exactly the same. It's the same exact formula. The only thing that really changes is the degrees of freedom calculation. So in tests for independence, the degrees of freedom changes so that it's R minus 1 multiplied by C minus 1. So the introvert-extrovert example versus colors, so we have 2 rows, introvert-extrovert, so 2 minus 1, that's 1. And then the C minus 1 would be, we had 4 colors, so it would be 4 minus 1 is 3. So 3 multiplied by 1 is 3. So degrees of freedom at 3 in this case. Let's talk about another example in using the chi-square test for independence. We have the null hypothesis that states that in the general population there's no relationship between gender and willingness to use mental health services. For the alternative hypothesis, we can state in the general population there is a consistent, predictable relationship between gender and willingness to use mental health services. So first things first, what's our degrees of freedom, our alpha level, and what is the critical value? Our degrees of freedom, remember, is R minus 1 multiplied by C minus 1. And our alpha level is 0.05. And our critical value for our chi-square, we can look up on a chart. In this case, I jumped ahead, is 7.81 again, because we have 2 genders, right? So 2 minus 1 for the rows, and then the columns, for this case, it had 4 values for an individual could endorse. So that's 4 minus 1, which is 3. So 3 multiplied by 1 is 3. Oh, it's 3, sorry. So 3 minus 1. So let me go back. So it's actually 5.99 in this instance. Okay, so let's go ahead and calculate. We first compute our F sub E, so our expected frequencies. So we need to fill in this box based upon our observed frequencies. And so for our 60 males, we calculate 20% of 60 equals 12 males probably would say they probably would not seek services, and then 30 males may seek services, and then 18 males would probably seek services. For our 90 females, we can calculate 18 females would probably not seek services, 45% would probably seek services, and then 27 females would probably seek services. And then we can calculate our chi-square statistics based upon the resulting frequencies. So it's the same formula as before. We have our observed minus our expected squared over the expected, and then the summation of this is 8.23. So in this case, we would definitely reject the null. But we also need to measure effect size, because it's not enough to say significant, but how significant. So the phi coefficient and the Kramer's v are probably the effect sizes of choice for chi-square statistical testing. The phi is calculated as the chi-square test value over n square root, and Kramer's v is calculated as the chi-square test value over n multiplied by the degrees of freedom square root, where degrees of freedom is the smaller value of R minus 1 or C minus 1. So you would insert the smaller value of R minus 1 or C minus 1 in that equation to calculate the Kramer's v. But how do you interpret v and Kramer's v? For v, Cohen provides a table of guidelines for interpretation. So with if you have the degrees of freedom of 1 that you're inserting into that equation, it says, v value of 0.1 is small, 0.3 is medium, 0.5 is large, etc. And then for the phi coefficient, it's a 0.1 is small, a 0.3 is medium, and a 0.5 or larger is large effect. So you notice that the phi and the Kramer's V are pretty much dead on when you have a degrees of freedom of 1 that you're inserting into the equation for the Kramer's V. So there's no difference there. It's when you get into larger degrees of freedom and more complex chi-square designs that they start to diverge. So whether to choose phi or V. Use phi when you have 2 dichotomous variables. So a 2 by 2, such as this, male, female versus candidate A or B. And use V when you have 2 variables or more with more than 2 levels. So that both variables need to have more than 2 levels, because if you have one with just 2 levels, then you still use the V. So both variables need to have more than 2 levels. Okay, well that was a brief presentation of the chi-square statistic, and good luck.